right, welcome to the Seafloor Spreading blend space activity. So we are going to do a flipped classroom for this lesson. And so you've already done your projects and you guys have already kind of started on this. So we're going to go through the composition of the ocean floor as well as the evidence for seafloor spreading and the overall process. So I have this cute little video here, but we'll watch that in class. So we'll kind of just skip over that real quick. All right, so in the last chapter, we talked about the difference between continental crests and oceanic crests. So the oceanic crest is much denser. If you look here, it's more concentrated, and the continental crest has a lot more air pockets and is lighter. Still pretty dense, but not as dense as the oceanic crest. So oceanic plates are heavier than continental plates. The oceanic plate is made up of basalt and covers the ocean floor, forms ocean basins. Basalt forms when lava reaches the surface and cools. Okay, so there's a lot of erupting underwater volcanoes, and we're going to talk about how that happens in just a bit. All right. So the ocean basin features. What would we do if we drained all of the water in the ocean? The ocean floor is covered with underwater mountain chains called the mid-ocean ridge, which is the longest chain of mountains in the world. So we would see these underwater mountains. And if we look at them closer, we can see that this is the area where the seafloor is spreading apart. So the mid-ocean ridge is where the seafloor is being pushed up and new ocean floor is being created. So how do we know all of this? So we haven't really explored much of the ocean floor physically, but we can detect a whole lot just by using sonar. And sonar is a device that bounces sound waves off of underwater objects, and then it records the echoes of these sound waves. So we can see where, depending on how the waves are bounced back towards the sonar devices, we can kind of map out the ocean floor, and we can see all the different mountains and the ranges, and all of those things are able to be detected through the use of sonar. So Harry Hess was a geologist that started to study the mid-ocean ridge. He said that at the mid-ocean ridge, molten material, known as magma, rises from the mantle and then erupts. The molten material then spreads out, and it pushes the rocks that are already there, so the older rocks pushes them aside, and so then new ocean floor is made, and he called this process seafloor spreading. And there's another video here, or I can mute it.
But the huge molten core contributes something else essential for life on Earth.
Of the magma.
A way of helping to regulate the planet's temperature. It's a remarkable system.
Actually, this is a video from that movie.
Magma, heated by the core, rises towards the Earth's surface.
It rises up.
As it spreads sideways, the Earth's crust is very slow.
The older rocks pushes them to the side, and new ocean floor is formed because as magma rises and reaches the surface, the ocean is cool, and it causes the magma to cool and form basalt. And so then you have this new ocean floor that kind of spreads out. And then as it's spreading, though, once it reaches a certain point, it does get recycled. So it does. Oceanic crust is much denser, so it's going to fall underneath that continental crust and just be recycled, and that process goes on and on and on. So,
dragged apart.
Pretty cool. This is called a convection current.
This moves the continents,
shifted. So,
creating the Earth's restless, ever-changing surface.
Part the continents to their present locations and continue to move just a few centimeters every year. Okay, so as the molten material rises from the mantle at the mid-ocean ridge, it cools, which forms new rock, and the old rock is pushed away like a conveyor belt. Okay, so this is another video of the
But while some
magma
plates crash together,
surface
others tear apart.
the ocean floor.
It happens under the ocean,
Process here.
like here, in the middle of the Atlantic.
So
Lava erupts at the boundary between two crustal plates.
as well.
The ridge is a line of underwater volcanoes, and it's here that new oceanic crust is formed.
This is where
It stretches from the South Atlantic all the way to Iceland in the north,
being pushed out,
where it rises above sea level.
then we can actually see the mid-ocean ridge.
From the air, the mid-Atlantic.
So how can the ocean floor keep getting wider? The ocean floor doesn't just keep spreading. The oceanic plates plunge deep into the water columns in the ocean trenches. So we do have like the recycling, like we were talking about, recycling of the ocean floor. So at the subduction areas, the oceanic crust is going to be pushed down because it's heavier, so it goes underneath the continental crust. If we go back here, subduction, the process by which the oceanic crust sinks beneath a deep ocean trench and back into the mantle where it is recycled. And just a reminder, I'm speaking very fast, so you should be pausing, going back, making sure that you are writing down all of this into your notes. Okay, so I will not be sharing this Prezi with you because I'm sharing the video. So it is your responsibility to obtain these notes because you can watch this video as much as you want. So just a quick reminder. So subduction in the Pacific Ocean. The Pacific Ocean is shrinking. It has many deep ocean trenches. And remember, the deep ocean trenches are where we see subduction. We see the oceanic plate sinking under the continental plate. So this happens in the Pacific Ocean, whereas in the Atlantic Ocean, it's expanding because this is where we have fewer trenches and there's more spreading of the ocean floor as opposed to subduction. So there's that big difference. So the Atlantic Ocean is expanding while the Pacific Ocean is shrinking. So then we have the different pieces of evidence for seafloor spreading. We can look at the new rocks. Hold on a second. This is not showing for some reason. So if we look at the different if we look at the composition of the ocean floor, we can actually see that, and we're going to speak about this in class tomorrow, that we have evidence of magnetic reversal. So whenever the magnetic field reverses, it's actually recorded into the rocks. So we can see that there's layers in different times where the magnetic reversals were recorded. We'll talk about that in class because it can tend to be a little difficult, but the evidence from magnetic strips, so it's just the rocks that record the reversals of the Earth's magnetic field at the time. We can look at the samples of the ocean floor and we can see that the older rocks are found farther away from the mid-ocean ridges and the younger rocks are in the center or away from the ridge. I'm sorry, at the center, the older rocks are away. Sorry about that. I know there are students coming in and hold on. Hold on one second, I'm doing a video. Can you just stand out there and make sure nobody comes in for me?
Yeah.
Hi! So then we also have the third piece of evidence is that we are able to see earthquake patterns. The patterns are observed around deep ocean trenches, and it's what happens at subduction zones. So we have earthquakes at subduction zones, and we're able to verify that. Near the deep ocean trenches is where the oceanic lithosphere is sinking, because we have earthquakes and that's what happens, right? And that concludes the entire lesson just in time because my other class is coming in.